So the first fluid structure to draw is BeF2, and we are told in this one that beryllium is electron deficient, so it's only going to have those 4 valence electrons. So the first thing we'll do is we will count our valence electrons. We got beryllium with 2, and fluorine with 7, and another fluorine with 7, for a total of 16 valence electrons. Of those 16, 4 are unpaired, which gives us a hint that we're probably going to have 2 bonds. And we're going to put the least electronegative element in the middle. Since fluorine is the most electronegative, that means beryllium is the least electronegative of these 2. So we'll go ahead and attach it to 2 fluorines. We'll give the outside or the terminal atoms their total of 8. Here are already 2, here are already 2. So each fluorine just needs 6 more. 1, 2, 3, 4, 5, 6 to give him 8. 1, 2, 3, 4, 5, 6 to give him 8. And as we were told in the prompt, this beryllium is electron deficient. It only has 4 electrons, which are there's 2 and there's 2. So we know we've drawn the correct structure. The next structure is BeCl3, and again we're told this one's also electron deficient. In this case it's boron, and boron will only have 6 valence electrons, which is fairly common for boron. So we'll draw our dot structures so we can get to thinking about it. Boron's got 3 valence electrons. Chlorine has 7. And the third chlorine has 7. So let's see, that's 21, 22, 23, 24 valence electrons. Of those, I see that 6 are unpaired. So this is giving me a hint that there's probably 3 bonds. Again, the least electronegative element will go in the center. In this case, that's boron. Go ahead and surround it by 3 chlorines. Give the outside or terminal elements their 8. There are 6 to give him a total of 8. 6 and 6. So just checking our work, this chlorine has 8, this chlorine has 8, this chlorine has 8, and boron we were told was electron deficient with 6, which he has, so I'm feeling good about this. And I actually didn't do this in the first one, but we should check our work here. Did we use exactly 24 electrons? Here's 8 plus 8 plus 8, which is 24. So we know that we are correct. The next one is CCl4. Carbon's got his 4 valence electrons. Each chlorine has 7 again. So let's see, that's a total of 32 valence electrons, of which 8 are unpaired, which tells me we might have 4 bonds here. Carbon is the least electronegative of these elements, so he's going in the middle. Go ahead and surround him by those 4 chlorines. And again, we'll give the outside ones their full octet, so they need 6 more each. And just to check, carbon in the center should also have 8. Here's 2, 4, 6, 8. So we are feeling good about this. So we'll just check our work. Did we use exactly 32? Here's 8 plus 8 plus 8 plus 8. So that's 32. So we know that we did this one correctly. Our next one is PBr5. And you can already be thinking here, you have 5 bromines attached to this phosphorus. This is going to be an expanded octet, and that's where our rules for dividing our unpaired by 2 kind of start falling apart. But we'll go ahead and just think about it. We got phosphorus with its 5 valence electrons, bromine with 7. So we've got those 5 bromines with 7. So that'll give us 35 from the bromines plus 5 from the phosphorus for a total of 40 valence electrons. Now, we can see that there are 1, 2, 3, 4, 5, 6, 7, 8 unpaired electrons here. So that implies there's only going to be 4 bonds, but we know that has to be wrong because this phosphorus has to be connected to all 5 bromines. So we're just going to be smarter than our method here. Let's connect this bromine, or these 5 bromines, to the phosphorus. So 1 up, 1 down. Now I'm going to kind of try to show these on a different plane than the other ones. 1, 2, 3 more bromines for a total of 5. If you kind of imagine, you have your poles, so like here's your north pole, if you want to think of it that way, and a south pole. But I also want you to think about these 3 lying on a plane here, just so we can kind of, that'll help us in future lessons. But let's go ahead and give these bromines their 8 that they need. Since they each already have 2 that they're sharing with phosphorus, they each only need 6 more. And each bromine has 8, so yes, 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 and yes. And now phosphorus here actually has an expanded octet, which is fairly common for phosphorus. He has 10, and that's perfectly okay. So just to check our work, we should have used exactly 40. Here's 8, 16, 24, 32, and 40. So we know that we've drawn the correct structure. The next one is Si6. Again, we can already tell this is an expanded octet because you have 6 iodines attached to a single sulfur, so we need the dot structures for them. Okay, and you can technically skip this step as you get better and better at drawing Lewis structures, but it just helps in our accounting and planning. Let's see, we have 7 on each iodine, and there's 6 of those, so 7 times 6 is 42, plus 6 more is a total of 48 valence electrons. The less electronegative one here is sulfur, so we're going to put sulfur in the center. And we'll go ahead and surround him with 6 iodines. I always recommend you start, when you have an expanded octet, of 1 going up, 1 going down, and then surround the rest on a separate plane. And I'll kind of try and draw a little bit of a picture to help you see that a little bit better. So again, you've got kind of a north pole you can think of and a south pole you can think of. But then these 4 other ones are lying in a square on a separate plane from those going up and down. So we'll give those outside ones their full octet. So each one needs 6 more. And sulfur in the center is actually expanded his octet to hold 12, which again is very common for sulfur. So we should have used exactly 48. Here's 8, 8, 8, 8, 8, and 8, and 8 times 6 is 48. So we know that we are correct. All right, so on to something a little bit different. We have a BH2 with a 1- charge. So we have an ion here now that we're trying to draw. Let's just start like normal. And again, this one features boron, which is electron deficient. He's only going to have 6 valence electrons. So boron, 1, 2, 3 currently. Hydrogen with just a single one. Hydrogen with a single one. But then we have to think about what this charge means. Since this is a negative charge, that means we've gained an electron on this ion. So we have 1 additional electron to work with here. So there's 3, 4, 5, 6 valence electrons. Okay, so let's go ahead and put the less electronegative element in the center. But in this case, we know that hydrogen can't go in the center. Hydrogen can only hold 2 valence electrons, so he can never be the center element. So we'll put boron in the center, surround him with 2 hydrogens. And ordinarily, we'd come over to these terminal or outside atoms and give them a full octet. But like we just said, these 2 are all hydrogen can hold, so he doesn't get any more unpaired electrons. But we've only used 2, 4, we need to use 6. So in this case, those 2 extra ones are going to go on to that boron. To finish this up, since we've used exactly 6 and everyone has an octet, even though boron only has it 6, since it's an ion, we have to put our Lewis structure in brackets. And let me get this out of the way a little bit. Oops, erased my 2. We'll put it in brackets and we'll notate the charge of that ion outside of those brackets. Next is in I3. Nitrogen has 5. Iodine has 7. So that's a total of 21 plus 5 is 26 valence electrons. Of those, we have 3, 4, 5, 6 unpaired, which leads us to think we're going to have 3 bonds. And we've got nitrogen going in the center. Go ahead and surround him with 3 iodines. And we'll give the outside ones their full octet, like normal. And then we can do some counting. We've used 8 here, 8 here, and 8 here for a total of 24, but we need to use 26, so those last 2 have to go on to that nitrogen, which is actually good because that gives nitrogen his full octet. So everybody has an octet, and we used exactly the right amount of valence electrons. Our next one is ClF4 with a 1 plus charge. So we've got another ion. Let's go ahead and get the dot structures for these. And there we've got them. All of these have 7. There's 5 of them, so that's 35 valence electrons to work with. But we've got to think about what this 1 plus charge means. This is a cation, so we've actually lost one of these electrons from to something. So we actually only have 34 valence electrons to work with. Out of these 2, chlorine is the less electronegative, so he goes in the middle. We'll go ahead and surround him by those 4 fluorines. We'll give those 4 fluorines their full octet. Now we've just got to check our work. We've got 8, 8, 8, and 8 for a total of 32, but we should have placed 34, so those last 2 are just going to go on that center element, which in this case is chlorine. Last step here, since it is an ion, we will have to put it in brackets and give it a 1 plus charge. And that brings us to the last one, which is SF5 with the 1 minus charge. There are dot structures. The fluorines have 7. 7 times 5 is 35, plus the 6 from sulfur is 41. But this is an anion, so it's gained 1 more. So we actually have 42 valence electrons to work with. And you can tell we've got another expanded octet because this sulfur has all 5 fluorines attached to it. So we'll just throw sulfur in the middle. Go ahead and attach the 5 fluorines to him. Give those fluorines their full octet of 8. All right, and we'll check our work. We have used 8, 16, 24, 32, 40 of our 42. And like always, when you have leftovers, they will go on to the center atom. So there's the Lewis structure for SF5 with the 1 minus charge. We just need to finish it up with some brackets and the charge. Let me clean that up because that looked terrible. There we go.